This video is a general introduction to a logic programming language called Prolog. We'll first study the basics and operators, then some advanced topics. Prolog is a very popular logic programming language, though logic programming isn't as popular as other programming paradigms. Why do we study Prolog? First of all, Prolog, or logic programming, is a logical choice in certain domains and tasks, such as security and argumentation. And because logic programming is so different from other programming paradigms, I think you'll be fascinated to learn how logic programming works. And also it might give you a new perspective on what programming is. Like anything you learn in this course, after this class and after doing an assignment, you'll be prepared to study Prolog in depth if you want it. And here's a brief history. Kowalski in late 60s showed that logical proofs can be done through computation. In early 70s, the earliest version of Prolog was developed to do syntactic parsing and natural language processing. In mid 70s, Warren developed the first version of Prolog that's considered efficient. Prolog uses first order logic, so you have predicates and terms, and every program is a set of horn clauses or implications. With or without premises. So when you don't have premises, that's just a fact that you state. And when you do have premises, then it becomes a rule, which you can use to infer other facts. And when you infer stuff, it's done by a resolution algorithm, and resolution is done by searching using backtracking with unification. The main components of Prolog are fact, rule, and query, where fact and rule constitute a knowledge base, or a program. For example, we can say Abby is a parent of Bob, and then Bob is a parent of Chang. So these are our facts. And we can also say X is a grandparent of Y, if X is a parent of someone and that someone is a parent of Y. Then we can query things like is Abby a grandparent of Chang? We can also say who's a grandparent of Chang? When it comes to the syntax, predicates and atomic terms start with the lowercase, and variables start with the capital letter or underscore. And you want to use what's called an anonymous variable when the value is never used. So if you look at the example we've been looking at, these are atomic terms. And these are variables. And these are anonymous variables. So here's an example where we have 8 clauses. So Atlanta is located in Georgia, Houston in Texas, Austin in Texas, Toronto in Ontario. So these are our facts. And then these are our rules. So the rules are something's located in Georgia implies that that thing's in USA. Something's located in Texas implies that that thing's in USA. So these are implications again. And once you have this knowledge base, here are different types of queries we can have. We can ask, is Atlanta located in Georgia? We can also ask, what's located in Georgia? Atlanta is located in what? So X is located in Y. So all pairs of X's and Y's where X is located in Y. And then this would be all X is such that X is located in itself. So based on our knowledge base, there will be no such a thing. What's located in USA? So when I run this, it says X is Atlanta. So Atlanta is a term that would make located in X, USA true. And if I press next, it gives you another thing. X could be Houston, and X could also be Austin. So these are the three terms that can make located in X, USA true. So what's happening underneath? How is Prolog finding these three terms? So when you ask the query located in X, USA, here's a derivation tree. So you have located in X, USA at the root. So there are no facts that matches this, but we have two rules whose conclusions are what we're looking for. And we're using backtracking search. So we first try the first rule. So we're making a query again, but now with X, Georgia. And then we do find a fact. So that's where you find X equals Atlanta. And then you backtrack and you try the second rule located in X, Texas. And then you find two facts, which gives you Houston and then Austin. Be careful. Group the predicates. So put mothers next to each other and fathers next to each other. Okay, now for the operators. The AND operation is done by comma. Okay, so suppose we want to find Michael's father and Michael's father's father. So our query becomes father f, Michael, father g, f. And when we run this query on some family tree, we get f is Charles Gordon and g is Charles. So Charles Gordon is Michael's father and Charles is Charles Gordon's father. When we reverse the order of these two, we would get the same answer, but the computation will take a lot longer because there are a lot more clauses that satisfies this. So the order matters in terms of efficiency. Or can be expressed using semicolon. So if you want to find out someone who's the father of Michael or Joy, then we can do father f, Michael, semicolon, father f, Joy. And negation, which you can do using the words not or /plus. And you can use this in front of any clause. For example, if you want to define non-parent xy, you can define it as not father xy and not mother xy. And not can be replaced with /plus. And when it comes to checking equality, one equal sign and two equal signs don't do the same thing. So when you have one equal sign, it succeeds when the arguments can be unified, whereas the double equal signs checks if the arguments are identical. So for example, suppose we want to define a predicate called parent of Katie. So we're checking whether X is a parent of Katie. The most straightforward way would be, you can define parent of Katie as parent X, Katie. If you want to use the equal sign, then we can do Y equals Katie and X is a parent of Y. This is fine. But if you did the double equal signs, what this does is it checks whether Y and Katie are equal, which is not the case. So this wouldn't work. So say parent of Katie, if we define it as parent Diana, Paul, and that's it. If we change this to Y and then Y equals Katie, this would still work. Diana and Paul. But if you do the two equal signs, this wouldn't work. You'll see false, because Y is not the same as Katie. We can also do map coloring. So we have three facts stating that red, green, and blue are colors. And then we just have one rule called color map that says C1, C2, and C3 are all colors, and C1 is not the same as C2, C1 is not the same as C3, and then C2 is not the same as C3. And then we can query color map XYZ. Once we make this query, what would it return? Color map x, y, z. Then we get different combinations of red, green, and blue. Let's talk about some advanced topics. The first is list. So the empty list is just open and close brackets. And a general list is defined as head, bar, tail. So if you have a list A, B, C, this a shorthand for A bar tail, where the tail is B bar tail, where the tail is C bar tail, and the tail is an empty list. And you can also do A, B bar tail, or A bar tail, and so on and so forth. So if you're to define contains, first define contains, and if the head is the same as X, then you can say X is in the list, regardless of what's in the tail. And another check we want to do is to ignore the head and see if X is in the tail. And we make the recursive call here. Say our query is contains the lists containing 1, 2, and 3. So does the list 1, 2, 3 contain the value 4? The answer should be no or false. But if you ask whether it contains, say, 3, it would say true. And there's something called cut, and cut prevents Prolog from backtracking. We had the example of located in X, Texas, where when we run it, it says X equals Houston, and when we ask for another answer, alternative answer, it says X equals Austin. But if you make the query located in X, Texas, cut, then it will return Houston, and that's it. Same thing for contains function. So by adding a cut here, we're going to prevent it from returning multiple answers. So suppose our list happened to be 1, 2, 3, 3, so it contains 3 twice. Then when we run it, it's going to return true, and then true again, because there's a second 3 in the list, and then false. But if we put a cut, then when we run the same query, it returns true, and that's it. It just ended the search. So again, you can use cut to prevent Prolog from finding more than one answer. And you can define complex terms. Give it some name, and then list terms as arguments. And a term could be non-variables, variables, or even other structures. And once you have a structure, it's stored as a tree in Prolog. So the name becomes a parent, and the parts become children. So for example, we can define a structure whose name is CS department, which has one child, which is another structure called student, which itself is a structure with 3 children, ID, name, and date of birth. The date is also a structure with date, month, and year. Suppose there are facts in our knowledge base. How do you find students who are born before 1995? Well, one way is we locate variables for what we're trying to identify, and then put a condition that the year has to be less than 1995. So we have Bobby, who was born in 1993. And if you're just interested in the name and year, then you can use anonymous variable. So instead of ID, we'll have anonymous variable. And same thing for day and month. We get Bobby 1993. So this was a brief introduction to Prolog. And if you're interested in learning more about Prolog and its advanced features, there are a lot of resources available online, so feel free to take a look.